All right. We're moving on to 4-4 today. Hopefully, you got a chance to look at 4-3 on Friday and did some synthetic division, because we are continuing on today with more polynomial stuff. We're going to use synthetic division today in some of the things that we do. Tomorrow will be review day, so if anybody's going to be gone tomorrow, let me know. I'll get you the review today. And then Wednesday will be our next quiz. Okay, it'll be over the first 4 sections of chapter 4. Then we got 2 more sections to cover. Next week, just looking ahead, test-wise, we don't have school Monday. This is the end of the 9 weeks, so halfway there. Tuesday will probably be a review day, and then I think test Wednesday, unless something happens between now and then. I think that's kind of the schedule we're looking at right now. Okay. All right. So, section 4-4. This is a continuation of polynomials. And we're going to talk a lot about polynomials as we continue on. Today, we're really going to be talking about the zeros. And last week, we did spend some time on this already. We found the zeros in a lot of scenarios, and we used our graph and things like that. Today, we're going to talk about how to find zeros other ways as well, and how to determine like what kind of zeros we have and how many zeros we're going to have and what do those zeros look like. Okay, and we talked about some of this stuff last week, but this will kind of just be a continuation and putting it all together a little bit. All right, so we're going to start off with 2 statements. When we talk about the zeros of a polynomial, there are 2 statements that we need to know. The first one, if a complex number is a zero, then its conjugate is also a zero. Okay, so a couple of words in there. Complex. When I say a complex number, what kind of number are we talking about? What makes a number complex?
Is that like a fraction?
Nope.
No.
Even though a lot of people think fractions are complex, right? Everybody remember that term, complex number?
Doesn't it like have a X,
Have an X in it?
Yeah.
Not necessarily. It's a good try. It is an imaginary number. Okay. A plus bi form is a complex number. Okay. So it's just, and we call it a complex number because when it's just 2i all by itself, that's an imaginary number. But when we add the real part to it, the real part with the imaginary part makes it a complex number. So if I said 7 plus 2i is a 0, then 7 minus 2i would also be a 0. Because conjugate's the other term that we talked about last chapter, especially when we did like division of a complex number. We said we had to multiply by its conjugate, and I told you we continue to see that word from time to time. We could also do it with like 8i. If 8i is a 0, then negative 8i is also a 0. So we talked about it a little bit last week, but whenever I have an imaginary 0, they always come in pairs. That you will never have just one imaginary 0. So if I've got 1, then I've always got its conjugate, so we have a pair of them. And so you will never have just 1. Okay, so that's the first statement. The second statement, if an irrational number is a 0, then its conjugate is also a 0. So those two statements are very, very similar, except one talks about a complex number, one talks about an irrational number. So what makes a number irrational? What's the most common type of irrational that we would probably see? So a rational number is any number that we can write as a fraction. So like 1/3 or 1/2 would all be rational numbers.
Like decimals.
What kind of decimals?
Huh? I'm not saying 6.7. Wait, imaginary decimals. Wait, that's the same thing as imaginary.
Yeah.
I don't know.
Decimals that don't end and don't repeat. Okay, so like 1/3 is 0.3 repeating. Okay, but it repeats, so it is not rational. Okay, or not irrational. Pi is a great example of an irrational number, but we typically don't see pi in college algebra, especially when we talk about zeros. So we're not going to use pi here. But what kind of irrational numbers would we see here? Well, it might be something like 2 minus radical 3. And then the conjugate of that would be 2 plus radical 3. Those would both be zeros. When they are a 0, they always come in pairs. And a lot of times the way we're going to see it is 2 plus or minus the square root of 3. We won't see them written necessarily always as two separate ones, even though we could write it as that. Or I could just do the square root of 11 and negative square root of 11. But if I were to take the square root of 11, I'm going to get an answer that goes on forever. It doesn't repeat. Okay? And most of the time, to get to these zeros, the i's or the radicals, we're going to end up having to go back to the quadratic formula to get there. Because we're going to have to write it in what we call the exact form. Radical 11 is the exact form. The decimal for it would be the decimal form, which is not an exact answer because it goes on forever. And so if we did round it to the decimal, and we kind of saw that in chapter 3 a little bit, where some of the problems on the test said, let's leave our answer as an exact value. And so we had to do the quadratic formula to find those exact values. All right, so here's the first example that we're going to start with. Write a polynomial in standard form with zeros of -1 and 3i. Okay, so first up here, if I wanted to say or list out my zeros, the only ones that come in pairs are imaginaries and radicals, okay? -1 is not an imaginary or a radical, so it doesn't have a pair. Okay, so if I say that -1 is a 0, that doesn't make +1 a 0. It doesn't work for integers or whole numbers. It only works for imaginaries. And so the trick here on this one is if I say 3i is a 0, even though only 2 of them are listed, -3i is also going to be a 0. Okay. And sometimes it may list all of them out, but if not, then we need to know if I already have an I, I know there's also going to be another I, because I can't just have one. Okay, so the first thing we're going to do here, standard form is the form we want it in, but we're going to start with factored form. When we write factored form, we always go x minus whatever the 0 is. So x minus -1 would really make this x plus 1. If I set that equal to 0, it gives me my 0, right? And so that would give me x equals -1. Then my two imaginaries would be x minus 3i and x plus 3i. Last week we talked a lot about the difference between factored form and standard form and graphing out of both and doing some different things with both, finding the zeros and that kind of thing. If I just left this in factored form, it would be pretty easy to do. Okay, we write the factors out and we're done. But we got to take this and write it as a normal polynomial. And when we do that, we think, well, because we have i's right now, we're going to end up with some i's. But what you'll find out is when we do this, the polynomial is going to look just like a normal, any old polynomial would look. So, when we do this, we're going to do some multiplying. And here's the first trick. Always do the conjugates first. Don't try to multiply x plus 1 times x minus 3i. I mean, you could FOIL those two, but it gets to be very, very complicated if you do that. Okay, trust me. I'm not going to do it that way. I'm not going to show you that way because it gets complicated. The easiest way to do it is always do the conjugates first. So we're going to leave x plus 1 alone. And then here, we're going to FOIL these two together. So x times x would be x squared. And then, even though it does look a little complicated, what's going to happen here, we'll make sense of it here in just a second, plus 3ix minus 3ix minus 9i squared. Okay? Kind of looks complicated, but because these two are conjugates with one another, the two inside should always cancel out. And then we see another thing that we've talked a lot about. I squared is really negative 1. So this is really negative 9 times negative 1, which would be a positive 9. So this whole thing becomes x squared plus 9. So we had some i's, but now all of a sudden the i's are gone. We don't have i's anymore. Okay, and that's going to happen whenever we multiply the two conjugates together. And then I got to FOIL one more time. So we're going to do x times x squared plus 1 times x squared plus 9 times x plus 1 times 9. And that's our polynomial in standard form. Okay, I'm not going to put this into my graph, but I like kind of drawing some connections between what we did last week and what we're doing today. When I tell you that this one has zeros of negative 1 and then positive 3i and negative 3i, I don't know exactly what this graph's going to look like, but it's going to look something similar to this. It's going to cross the x-axis at negative 1 because that's one of my zeros. It will never cross the x-axis again because my other two zeros are imaginary. So immediately when I graph this, I know that I have one real zero and two imaginary zeros. And the reason I tell you that is because we're going to also go the other direction. I'm going to give you this, and I'm going to ask you to find what the other zeros are going to be, and we're going to have to go the other way with it as well. So if I give you the zeros, we can come up with the polynomial, but if I give you the polynomial, we're also going to have to come up with zeros. It's kind of like going from factoring to a polynomial, but polynomial back to the factors. And same idea here. All right, this next thing, I'll kind of start by saying that we won't use this theorem a lot, okay? And we talk about it mainly because it usually shows up on the final, so it's definitely something we need to cover. But when I took college algebra, I used this theorem a lot because we had to, and I'll kind of talk about why. But we really don't use this much anymore. And so we're going to talk about it, but just know that we're not going to see it a ton. Call it the rational zero theorem. And what this does is it gives me all possible rational zeros. But the reason why it's not really beneficial anymore, or as beneficial as it once was, is because your list of possibilities might be like 12 different possibilities long. But maybe there's only 2 actual rational zeros. And so we have this big long list. And the reason we don't use this as much anymore is because of technology, right? We have graphing calculators now that I don't need to kind of check to see what zeros work. I can just look at my calculator and know this crosses the x-axis at 2. So I know 2 is a 0. We don't necessarily have to limit down our zeros. But here's how it works. So I'm going to give you the generic form of an equation here. This is our leading term. Last week we talked about putting our polynomial in standard form. So the leading term is the term out in front, and then a sub 0 is what we call the constant. It's the one thing that doesn't have an x attached to it. We're going to call this our p-value, and we're going to call this q, this leading coefficient, our q-value. So p is going to represent any factors of the constant. Anything that goes into that constant. Q is going to be the factors of the lead coefficient. So whatever number is out in front, there's going to be some number here that's going to represent our Q value, and we're going to find all the factors of that. So if I happen to have like a 12 right here, I would list all the things that go into 12. So my list would be a little bit longer, right? Because there's quite a few things that go into 12. So the more factors you have, the harder it becomes. And then we're going to take P divided by Q. So we're going to take all the factors of P divided by all the factors of Q, and that would be all possible rational zeros. And here's the other thing, is this is limited to only the rational zeros. This isn't going to give us like imaginary zeros or irrational zeros or any other zeros that we have. It just is limited to the rational zeros. So that's why, another reason why it's not very helpful in a lot of scenarios. All right, so I'm going to do an example here. I'm going to give you a polynomial. And the only thing that we need are the p-value and the q-value. So a little bit easier when we have some numbers in here. We don't need all this stuff in between. You do want to make sure that it's in standard form, right? We want to make sure we're starting with the highest and going down to the constant. Just like any other time that we have a polynomial, always make sure it's in standard form. But as long as it's in standard form, the end is our p, the beginning is our q. So we're going to take all the p-values divided by all the q-values. So my p-value is 4. And what I'll tell you about the signs is we're not really going to be concerned with the signs because on our answer, we put plus or minus on our answer. So really we're just saying what numbers go into 4. Don't necessarily worry if it's a positive or a negative 4. So things that go into 4 would be 1, 2, and 4. Those are the factors of 4. Okay, the q value is 3. So the factors of 3 are 1 and 3. So we don't have a ton of possibilities there. And I kind of did that on purpose because I didn't want to give you one with a bunch of possibilities. But we have to take all the numbers on top divided by all the numbers on bottom. So I kind of like to just organize it and say, let's take all of these and divide it by 1, first of all. So if I divide all of those by 1, 1 divided by 1 is 1, but we're going to put plus or minus on our answer. And then 2 divided by 1. And then 4 divided by 1. And then we're going to take all those numbers and we're going to divide them by 3. So we're going to go 1 divided by 3. 2 divided by 3. And 4 divided by 3. So we have 6 different values, but not only do we have 6 values, we really have 12 possibilities because we put plus or minus on each number. So we have 12 different things that could be rational zeros. Well, if I go back to the beginning here, this is a 4th degree polynomial, right? So the most zeros we can have, based on what we talked about last week, is 4. 4 is the most zeros that I can have. Can't have more than that. So obviously not all of these are going to work. So how could this be used? Well, like I told you, when I took college algebra, which been a while now, we didn't have graphing calculators as readily available as you guys do now. And so here's what we had to do. To see which ones of these were actually zeros, we would go to synthetic division. I would put 1 into synthetic division, and I would see if we got a remainder of 0. And if we got a remainder of 0, then boom, it worked, right? And I would keep going until I found something that worked. And then we would have to just find some rational zeros. Well, there's 12 possibilities there, so you could be looking for a while, right? So not a super ideal. I'm not going to ask you guys to use this a lot because now we can just put this into our calculator. I can find a couple of places that it crosses the x-axis, and I can match it up with something from this list, okay? So that's what I'm going to do here real quick. I'm going to show you, and that's another reason why this is kind of hard to like say all of your zeros are from this list. No, this list only gives you the rational zeros. It's not going to give you imaginary. It's not going to give you irrational zeros. It's just giving you integers or whole numbers or rational numbers, fractions. Okay, so like I said, we're not going to use that a lot, but we will have a problem probably on the quiz next week and probably again on the test, mainly because we're going to see that on the final, and so I want you guys to make sure you know how to do that when it comes time to do that on the final at the end of the semester too. Okay, what we're going to spend the rest of the time on is kind of where this all ties together. Okay, and this is going to be kind of doing all the things that we've doing leading up to what we've got today. For this first one, I'm going to give you a polynomial. Sometimes they'll give us a 0, sometimes they won't. Okay, and this one, they're saying, here's my polynomial, and we know one of the zeros. Find all the zeros. And the other thing I'm going to add to this is we always want to write our answer as an exact answer. And I'll tell you why here in just a second. Because what most people would do is they would just put this into the calculator. They'd look at where it crosses the x-axis, if it crosses it 3 times. And sometimes the other 2 solutions might be irrational decimals, right? That's when we want to write that answer as an exact value. So for this one here, we have a cubic polynomial, so we have 3 zeros that we got to account for, okay, in some shape or form. And we're going to do a couple of different examples about this today. So because we know that -5 is a 0, I mean, if you want to, your first thought could be maybe I can just graph this and maybe all of my zeros are nice whole numbers, right? And we know they're not imaginary, so that's good news. They're going to be irrational because of those decimals that we got. We're going to go back to what we did on Friday, synthetic division. We're going to put -5 in the box. Okay, it's a 0. So if it's given to me as a factor like x plus 5, then we always do the opposite. But if it's given to me as a 0, the 0 is what goes in the box. We're going to write down our coefficients. And I know I wasn't here on Friday, so if you guys have questions about synthetic division, make sure, let me know today, and we can kind of talk about anything that you're not sure about. We're going to bring down the 1. Negative 5 times 1 is negative 5. 5 plus negative 5 is 0. Negative 5 times 0, 0. Negative 2 plus 0, negative 2. And then this last number here is always our remainder. If I tell you that negative 5 is a 0, we better get a remainder of 0. Okay, if I don't get a remainder of 0, I have done something wrong. Hey, we have to get a remainder of 0. So that all looks pretty good because we get a remainder of 0. Now we're looking for our other two zeros. Whenever we do synthetic division, we're trying to do is we're trying to break this polynomial down into a smaller polynomial that we can work with. So we started with a cubic polynomial. We're going to take what's left over right here, and we're going to write this as a quadratic. We're going to drop it down in a degree. So we started with cubic, so now we're going to go 1x squared. I don't necessarily need to put the 1 in front. So 1x squared plus 0x is another thing I don't necessarily need, right? There's no reason to put a 0x in there, so I'm going to write it as x squared minus 2. That is now my quadratic equation that we get from breaking down the original polynomial. And now this is a quadratic, so now we got to solve this quadratic equation. What would be the best way to solve this quadratic? We can't graph it because we already know that the answers are decimals. Could, okay. So quadratic, you can use it every time, okay? But there's an easier one on this one. Because there's no b value, what would be the easier way to go on? If this was a perfect square, DOPS would work. You're right. Okay, but since it's not a perfect square, we can't do DOPS. Yeah, just do the square root method. Add 2. Take the square root. And we get plus or minus the square root of 2. Okay. So negative 5 and plus or minus the square root of 2 are our 3 zeros. So we've now accounted for all 3 zeros. That's why plus or minus is such a big deal as well. I'm not going to pull the graph back up just for the sake of saving a little bit of time. But the two decimals we got just a few minutes ago when we typed this one in were positive 1.4 whatever and negative 1.4 whatever. That's the equivalent of this radical right here. Those would be the decimal answers. This is the exact or radical answer. Okay, so that would be one way we could approach this. Okay, questions on that? Okay, look at another one. This one is kind of along the same lines. But on this one, I'm not going to give you any zeros to start off with. So our go-to, just kind of like it was on quadratic, is when we try to find all zeros, the first thing we should always look at is where does it cross the x-axis? And in some cases, maybe all of the zeros, all 3 zeros that we have to account for, maybe they're all nice whole number or integers, right? Not always going to be the case, but it could be the case in some problems. Okay, but last one they gave us the 0 to start with. This one we don't have any, so we're going to go right to our calculator. So let's put this one in. Negative 2 and 1 are zeros, but how many zeros do we have to account for? 3. Okay, somehow we have to account for how do we get back to a cubic polynomial. We have to account for 3 zeros in some shape or form. So the first thing I'm going to do here is I'm going to put negative 2 in the box. And I choose the negative 2 because it goes through the x-axis at negative 2. The other thing you have to be careful of on synthetic division is this one is missing an x squared, right? And because it's missing the x squared, we're going to put a 0 in its place. We already know that it's a 0 because we found that out on the graph, right? So I have to get a remainder of 0 here again. Okay? If you don't get a remainder of 0 here, you have done something wrong. Make sure you understand that. If I know that it's a 0, I have to get a remainder of 0. Okay, and then what I'm going to do, we started with a cubic. We're going to break this down into a quadratic. So the quadratic equation would look like that. Okay, we're dropping it down a degree. 1x squared minus 2x plus 1. So square root method if there's no b value. We could do the quadratic formula, but what else could we do? What are some other methods that we talked about with quadratics? If it's a trinomial, I could do product and sum, right? Is there anything that multiplies to get 1 and adds to get negative 2? Negative 1, negative 1. Which we most of the time write as x minus 1 squared, because there's 2 of them. And so what that tells me, thinking back to what we talked about last week again, x equals 1 has a multiplicity of 2. And you remember when we said when it has an even multiplicity, that it bounces off the x-axis at that point? And sure enough, if we go back and remember what the graph looked like, it goes through the x-axis here, and then it comes back down, hits and comes back up. Okay, so this is a really important piece because otherwise I'm expecting 3 different zeros, right? Because it's cubic. But when I say that x equals 1 has a multiplicity of 2, that means that accounts for 2 of my zeros. That's why we have a cubic, but we only have 2 different zeros for this. It's really 3 because you could set this equal to 0 twice, but there's no reason to do that. Okay, questions on that one? I'm just trying to show you like some different cubics. Cubics are all created differently, right? I could give you one that has an imaginary solution. All right, so here's the last example of the day. Save the best for last, right? Good news, Ellie, right? Best for last? If you think you've had fun so far, hold on for this one. We got a quartic polynomial, which means I have to account for how many zeros? 4. Some shape or form, I got to account for 4 zeros. Find all zeros. So we got to find all 4 of them. We don't have any of them given to us. So the first step is always graph it. See if we can find any. We don't want to do the rational zero theorem. That's going to take forever, right? We want to limit down our possibilities. We want to find some in our calculator. There's 2 of the 4. I'm going to start with -1 first, just because it'll be a little bit easier to do that one rather than the 1/3. It's not a fraction. 3, -4, 1, 6, -2. But if I have 2 zeros, it doesn't matter which one I start with. I could have started with the 1/3. Both of them are zeros. And whichever one I choose to use, they both should give me a remainder of 0. I'll bring down 3. We get a remainder of 0. Okay, so that's good news. Here's the other thing that we can do with synthetic division. As long as we get a remainder of 0, which we should, now I can use the 1/3, and I don't have to start over. In fact, you don't want to start over. you're going to put the 1/3 next to these leftover numbers. And we're going to do synthetic division again with those numbers. And we're just going to repeat the process. Now, this looks like it's going to be really hard because we have fraction, but it's not as bad as what you might think. We do have to multiply 1/3 by 3, but when I multiply by 1/3, it's really like dividing by 3, right? So 3 divided by 3 would just be 1. And that would become -6. -6 divided by 3 would be -2, which is +6. 6 divided by 3 would be 2, and sure enough, we get a remainder of 0. If I knew 2 other zeros, I could keep going, but I don't, okay? This started off with a quartic polynomial. Then we broke it down to a cubic polynomial. Now it's a quadratic polynomial. Every time I go through synthetic division, I break it down by another degree. So the leftover here is a quadratic. Which would be this right here. And this goes back to chapter 3. Square root method we already did today. We could try to factor it, but this isn't going to factor. We've already determined that the answers are imaginary. So pretty much our only go-to method here is going to be what?
Quadratic formula.
This guy right here. Yep, that's our only option. So here we go. Just like riding a bike, just jump on, let's do the quadratic formula, right? X equals the opposite of B. So the opposite of -6 would be +6. B squared, -6 squared would become 36. Minus 4 times 3 times 6 all over 2 times 3. Okay, the part underneath the radical is probably where most of the issues are made, okay? It's because sometimes either we try to put it all into our calculator at once or we put something in wrong. This number always has to be positive, okay? I saw there a lot of errors were made last chapter right here, these numbers right here. 4 times 3 is 12, 12 times 6 is 72, 36 minus 72 would be -36. What is the square root of -36? 6i. Because we take the square root of negative, we get an I. Both of those are divisible by 6. 6 divided by 6 is 1. 6i divided by 6 is 1i. So 1 plus or minus 1i. And those are our two imaginary zeros. And going way back to the beginning of the lesson today, we talked about how when you have an imaginary zero, you have 2, and that's because of that plus or minus right there. 1 plus I and 1 minus I. You can write it as 2 separate zeros if you want to, but probably not. Easier to write it like that. Okay, I know throwing a lot at you here, a lot of stuff going on there. Here's the assignment for this one. I'll post answers tonight, but I will tell you guys once again, just you got to make sure you're doing these problems, doing these assignments to practice these kind of skills, right? Because you're going to get imaginary solutions. You're going to get radical solutions. You're going to get a lot of different types of polynomials. It'd be nice if they were all just nice integer answers, but that's not going to be the case on some of these. So you got to make sure that we're doing these and practicing them. Pay attention to the directions as well, because the directions will be different for